So here I have the Optris XI 400, and later I'm going to do some demonstrations with this camera. Okay, so to start, let's talk about how the thermal camera is constructed. A thermal camera is quite similar to a regular camera. As you can see in this image over here, we have the object that we're measuring, which emits infrared radiation, usually, and then we have some optics, which, for example, in this camera, you can see here, this is made of germanium. And then we have the sensor which reads the infrared radiation, and then we have the electronics that output the information, in this case via this USB cable. So starting from the optics of a thermal camera is obviously very important. It's what focuses the light on the detector. However, choosing the right material is quite hard, since many things don't have a high transmissivity in this frequency. So here you can see the graph. So there is transmissivity on the top, and on the bottom we have the wavelength in micrometers. So you can see that a good one is zinc selenide, and germanium is also good, because it's also important that transmissivity is quite flat. While, for example, here glass, which is on the top, drastically loses transmissivity at bigger wavelengths. It's important to select the right optics. Sometimes if you want a very high quality thermal camera, you will put an anti-reflective coating. This is also done in normal cameras, but in thermal cameras it can be more important, because reducing the reflectivity will increase the transmittance. So as I said before, here on this camera you can see the germanium lens with the anti-reflective coating, and so this helps the transmissivity. For the thermal detector, you can divide them in two categories. So there are thermal detectors. These are detectors that measure their own temperature and are heated from the optics and the concentrated IR light, and we have quantum detectors. So in the thermal detectors we have these three types: thermopiles, pyroelectric detectors, and bolometers, whilst in quantum detectors we only have quantum detectors. The first type is the thermopile. These are sensors that are heated by the focused IR light, and they work like a thermocouple. So they get heated on one side, and on the other side they're cool, and so you can measure the temperature of the detector. It's a quite common sensor, as it is quite cheap and easy to make. Another type of sensor is the pyroelectric detector. So this detector uses an interesting property of some materials, which is the pyroelectric effect. Basically, some materials, when you heat them, whilst they're being heated, they produce a voltage, and then they're cooled down, they produce another voltage. Make a pyroelectric detector, you must switch on and off the IR light so that the detector cools down and heats up, and by measuring the difference in temperature between the cold and the hot, you can understand how strong the IR light is. The last type of thermal detector is a bolometer, and so these use just to measure the resistance of some resistances, and based on the temperature of each pixel in the detector, the resistance changes. So really all of these thermal detectors are quite similar. They always have some way of measuring the temperature of each pixel. A detector that is significantly different is the quantum detector. Quantum detectors are more similar to the normal detectors in regular cameras. So these use the photovoltaic effect, and so when the IR light hits them, they produce a voltage which can be measured. They are usually made of semiconductor, and so they are very similar to a normal visible camera. The quantum detectors are used when you need something that is very fast. You can get much higher frame rates. For example, this XI400 uses a bolometer, and it can get up to a maximum of 80 Hertz, whilst quantum detectors can go in the hundreds of Hertz, though still not as fast as a regular camera. They are usually more expensive. The electronics of the thermal camera is quite simple. It's again very similar to a normal camera. You just need to measure the output of the detector, which can be resistance, voltage, depending on the type of detector, and you have to somehow interpret that as a temperature. If you design the electronics, you must always take account that the lens might not have the same transmissivity in all frequencies, and also the detector might not have a linear response always. Some thermal cameras, to reduce noise, are cooled down with the liquid nitrogen or liquid helium, but this is usually for very expensive, high-quality cameras when the measurements need to be extremely precise. So the physical principles of temperature measurement are quite simple. You have an object that when is heated or even at room temperature or below emits a certain amount of IR light. How much light it emits depends on the temperature and also on the emissivity. So for example, here we have this formula which says that the emissivity plus reflection plus transmissivity is equal to 1. So if you have an object with an emissivity of 1, then it will have 0 reflectivity and 0 transmissivity. Whilst if you have an object that is, for example, made of metal, it will have a high reflectivity and so a very low emissivity. Having a high emissivity makes the temperature measurement much simpler, and based on the emissivity, you could get some wrong results with the thermal camera. For example, you can have two objects that have the same temperature, but if one has twice the emissivity of the other, then that one will emit twice the IR light as the other one, and so will appear hotter. A useful analogy for this IR light is the black body, which is a theoretical object that has an emissivity of 1. Here in the bottom you can see a graph of how much radiation is emitted at different temperatures. The only thing I would note is that here there is like this spectrum that is drawn and it was mirrored. It's supposed to be the other way around. So the hotter an object is, the higher the smaller the wavelengths of light that it emits, but it also emits more light. This is why if normal objects don't glow in the visible, but once objects start heating up to roughly 500 degrees centigrade, you can start seeing them glow. First red hot and then eventually white hot, and if they're very hot, slightly blue hot. So measuring the temperature of reflective objects can sometimes present a challenge. As I said before, if you have a metal object, then it will have a very high reflectivity, and so usually you're not able to directly measure the temperature of, for example, the top load of this Tesla coil. So what you do is you have some stickers which have a very well defined emissivity, usually like 0.95, and you put them on the metal object and they will stay to roughly the same temperature as the object, and you can measure the temperature of the sticker. Another way is to create an object that is similar to a black body. So this is usually done by drilling a hole in the metal structure. However, this is rarely done as the hole needs to be quite deep. It has to be 5 times deeper roughly than it is wide. So of course, if you have a 2 millimeter wide hole, it will have to be a centimeter thick, and usually objects you can't drill into the object that you're measuring. So I will do some demos now, and so that we can see how to use the thermal camera. So first I will open Pixconnect, which is the software that is originally designed for this thermal camera, and then we will do it on DEWESoft X. However, it should be noted that for DEWESoft X there is a plugin for the thermal camera. So now I am opening Pixconnect. The thermal camera is already connected. This one is connected via USB. This is Pixconnect. I am removing the lids from the camera. The thermal camera can only run on one program. If you have another program trying to operate it, it will work in neither. So here we can see this room and how it looks with the thermal light. So here on this bottom bar we can adjust the focus, because thermal cameras very rarely have autofocus. So we can try to focus it, and this seems about right. Here we can choose how the temperature range is decided. I can of course go manually and change the temperature range, as you can see here. So this is the difference between the darkest color and the brightest color. So we can go here, it is just that the blackest color is the lowest temperature measured, and the hottest point is the highest temperature measured. We can go to 1 sigma or 3 sigma, which adjust the temperature in a different way. So here we can see a couple of things. There is someone waving his hand on the back. We can see that people are very easy to see with the thermal camera, as they usually are warmer than the surroundings. And if something that could be more interesting to see is, for example, the computer. So here we can see how the computer is heating up. So for example, the buttons on the keyboard are relatively cool, whilst the spot under the monitor is quite a bit hotter, and this is probably because the CPU is there. You can also see my reflection in the monitor, and of course we don't see the image projected on the monitor. You can also see that these webcams are using some electricity and are thus heating up. That is something I wanted to show is, for example, the Tesla coil. As you can see, if I try to measure the temperature of the Tesla coil, we just see the reflection in the top load of the Tesla coil. So for example, as you can see the reflection of my arm in the Tesla coil. So this can make measuring metal objects quite complicated, and as I said before, some special stickers should be used, but I like using tape. So we have placed the tape, and as you can see, the tape appears to be warmer than the top load, even though it's at the same temperature. And this is what I said before about the different emissivities of materials. So the tape has a much higher emissivity than the top load, so the top load will appear colder. Though in this case, it's actually just because we see the reflection of the colder roof on the top load, or I think it's the cold roof. Now I will show how to connect it in DEWESoft X. So let's close Pixconnect, the quantum detector. Yeah. So the quantum detector is a type of detector that is not a thermal detector. So whilst the other detectors measure basically their own temperature, the temperature of every pixel, which is heated up by the concentrated IR light, quantum detectors use the photovoltaic effect to generate some voltage when IR lights hits each pixel. So this makes them very similar to a regular camera. So since still DEWESoft X is opening, quantum detectors use a semiconductor. I don't open. So it's like a regular camera. Okay, so you have to go to channel setup, Optris. Here it's, yes, it was the pyroelectric effect. Yes, but well, the pyroelectric effect is different. So the quantum detector doesn't actually get heated, or doesn't intentionally get heated by the IR light. It only measures the intensity. The pyroelectric effect measures by how much it's heated. It's a very strange property of matter. So as I said before, some materials, if you heat them up, they generate a voltage while the temperature is changing. So once it's hot, it doesn't generate anything. If it's cold, it doesn't generate anything. When the temperature is changing, it generates some electricity. And so if you allow the light to pass and then block it repeatedly, then the detector will heat up and cool down, and using the pyroelectric effect you can see, calculate the temperature difference between when it's cold and when it's hot, and doing that you can estimate the temperature of the detector and so of the object that you're measuring. So it's slightly different. Okay, so we go to setup. This time we were lucky, it worked first time. Okay, so here we can see all the different settings. So we can change the frequency at which it takes images. So here it's at 27 Hertz. We can set it to 80 Hertz, looks about the same. Now here you can change the temperature range. So you can change the temperature range of which the thermal camera can measure. So we can go from -20 to 100 degrees centigrade. So this is what is usually used, as you don't normally have something over 100 degrees centigrade. If you want to measure something hotter, you can set it from 0 to 250 degrees centigrade. But now you can't measure the temperature of a freezer, for example. Usually the resolution drops slightly, but still kind of good. If you go from 150 to 900 degrees, then the image gets significantly worse, because it's made to measure things at more than 150 degrees. So here you can see that there is nothing to see. There isn't something at 150 degrees here. So let's set the temperature range from -20 to 100 degrees centigrade. So here we can change the emissivity of objects. So right now it's set to 1, and so the temperatures don't appear correct because nothing has an emissivity of 1. We can change the emissivity to, for example, 0.8, and then now everything should appear hotter. Ambient temperature, this is something which usually you shouldn't really change. There's no reason to change it. And here you can change the frequency. Again, this is basically the setting of the camera, and this is the specific frequency at which you're capturing, and the rest isn't that important. And here you can change the focus. One important thing to note is when you're in DEWESoft X, when you're measuring, you can't change the focus anymore. You can now go to measured areas. We can add something and add a point, but this is not necessary. So we go to OK, and for now let's only capture the first, which is the thermal image, and you can set the temperature range from -20 to 100 degrees. Now, if we go to measure, to see the thermal camera, we must add a 3D graph. and you can select the main frame. Usually we like to use the iron temperature range in color palette instead of the rainbow one because it's easier to understand the temperature. And usually you set the graph preview to 2D. And so now here is our image. I think it's slightly deformed, but that's easy to fix, like this. So here we can see everything, but as I said before, but you can see that everything seems roughly of the same color. So to do this, we can just press here to rescale the range, and it will look better. But something which is, let's say, it's better to do is to set here to click on auto scale so that it will constantly change. Though having auto scale is sometimes a bit confusing because, for example, as you can see here, the maximum temperature on the range is continuously changing and it's not very constant, the colors. But usually this is useful because you always have the temperature range that fits all the points. Now in DEWESoft X you only have that you can set the color palette range from minimum to maximum temperature, unlike in DEWESoft X where in Pixconnect where you can choose the 1 sigma and 3 sigma option. But this is usually not necessary. Try to measure the temperature of something. But before that, I would like to note, of course, this is a 3D graph, so if you set it to 3D and you look at the side, you can see that it's always a 3D graph. And this is kind of fun to see though. Usually, if you look at it like this, you don't understand very well what's going on, whilst looking at it from the top makes everything clearer. Okay, so now we can see some things. So with different objects, of course, have different IR properties. So for example, this is the cap of the thermal camera. This is some kind of plastic, probably HDPE, and so we can see that it is a bit transparent to the IR, and so we can see a low quality image. Though still the transmissivity isn't that high, so if I heat it up with my finger, we can see it getting warmer. As I noted before, the Tesla coil is very reflective, and so we can see the tape to measure the temperature. So again, one should not use electrical tape. There are specific stickers that I don't have to doing this, where you can get very precise temperature measurement. And so they're not only used on metals, but are sometimes used also on other objects when you need a very precise reading. For use cases of thermal cameras are very useful in many cases. Thermal cameras have many advantages over normal thermometers. So for example, thermal cameras measure the temperature of the object whilst a thermometer measures its own temperature, and so this allows for a faster response time. This is usually not necessary since usually temperature doesn't change very fast, but in some cases it's important. Second, you can measure temperature from a distance. You don't have to connect thermometers to every object in this image, and if you have objects that move around, it's useful to not have thousands of cables that you have to manage. That is also another advantage. You don't need to set up so many temperature sensors. So for example, in this image is roughly 300 by 300, okay, it's 288 by 382 pixels, so that would be a lot of thermometers to set up. These are the main advantages of a thermal camera. Usually the high speed is not necessary, but if you want to measure the temperature of a flame, I could say you would definitely get a much faster response time. And that brings us to another usually small advantage. You have a higher temperature range. So usually with thermometers you can't measure over like 2000 degrees Celsius, usually it's much less. But with these thermal cameras you can, well, not this one, but with thermal cameras you can measure to much higher temperatures since the thermal camera itself doesn't melt, since it's not exposed to that temperature. For measuring cold objects, it's not necessary to have special detectors really, so it doesn't present much of an advantage. Well, I've taken 40 minutes of time, so are there any questions? Yes.
When you set up the thermal camera and you set the emissivity,
yes,
you put 0.8, and why you choose the number there?
Well, so usually you would set the emissivity to 0.9 because it's roughly the emissivity of most objects, but I set it to 0.8 just so that you can see a greater difference between the 1 and the later 0.8. So actually, that we can change it again. Here on setup, the emissivity is 0.8.
So the transmissivity is bad because of the volume.
Usually objects don't transmit any, are not transparent in the IR range. It's very rare. So, for example, this cap is one of two things that I found that are transparent in the IR, at least slightly. So for example, this acrylic tube on the bottom of the Tesla coil, as you can see, it's not transparent. The other objects that I found is transparent are like the plastic bags. Those are transparent, but not that much because the material is very transparent, but because they are very thin. Okay. I mean, this is a bit thicker than most plastic bags, but we should be able to see the zip ties inside. However, we should adjust the focus if we want to get a more precise, a less blurry measurement. So as you can see here, you can see the zip ties inside of the plastic bag, and of course, if I heat some of the zip ties with my hands, then they get warmer. Or maybe it's the bag getting warmer, I'm not sure. I don't know how transparent this bag is. But again, as you can see, if I cover a person with the bag, it seems the person looks colder because the bag is colder and it's not perfectly transparent. So it's blocking some of the IR light.
I thought the emissivity plus transmissivity plus reflections, you get the negative reflections.
Because negative, you can't get negative reflectivity because 0 means that it doesn't reflect any light. Yes, you can calibrate them. The calibration files are inside the camera, so I mean when you get the camera, it's already calibrated, but I'm pretty sure that the manufacturer will calibrate the camera every year probably. Yeah, but again, the calibration means that the camera works well with the right settings. So of course, if you want to measure something, then you have to set the right emissivity. So if I set the emissivity of 0.1, everything should appear hot. You see, now it looks that 70 degrees, 80. Yes, there is a simple way, I would say. You grab the object and you put a thermometer on it and you measure its temperature. Say it's 30 degrees, and you change the emissivity in the thermal camera until the thermal camera says that it's at 30 degrees. So the correct measurement. So usually there is a simpler way, I guess. For most objects, if they're not transparent or they're not reflective, so for example, this laptop here, you can see it's reflective and you can see the reflection. So this does not have an emissivity of 1. The table is also reflective, but there are many things which are not reflective. So for example, the mouse is not reflective, and since it's not transparent, it should have an emissivity of very close to 1. And in fact, if I put my finger on it, you can immediately see the spot where I put the finger. Last thing that I will show, which I find interesting, if you have the thermal camera looking on the table, then if you pass your finger quickly on the table, it will get very hot. That's not really because of the heat conducting from your finger to the table, but it's from the friction between your finger and the table, heating the table up. And so it's interesting, you can basically draw on the table. Okay, I guess that's all. So thank you for listening.
Please keep in mind that to give a presentation in front of such audience is also